Welcome to the office. We want to continue taking a look at finitely generated abelian groups and, of course, direct products here. So let's take a look at an example now of our least common multiple. So if we have the direct product of some collection of groups, and if AI is of finite order Ri in the group, right, its associated group, then the order of this element in the direct product is equal to the least common multiple of all of the orders of the elements in this direct product, right, in this element of the direct product. The theorem itself is a little bit hard to read. When we look at an example of it, it should make a fair bit of sense to us. So let's consider the group Z12 cross Z15 cross Z14 cross Z9. In this group here, right, this direct product, we have the 1, 2, 3, 4 individual groups. So the order of 2 in Z12, right, 2 plus 2 equals 4, plus 2 equals 6, plus 2 equals 8, plus 2 equals 10, plus 2 equals 0, right, because we're working modulo 12. So Z12 there. The order of 2 in there is 6. The order of 3 in Z15, right? Essentially, the question is 3 times what gives you 15? Well, 3 times 5 gives you 15. So the order is 5. The order of, let's see here, 4 in Z14 is, oh, right, 4 doesn't divide 14. So how do we work with that? Well, if I want to find what the order is, I need to find a multiple of 4, right? 4 times what? Right, 4 plus 4 plus 4 plus 4. How many copies of 4 in that addition is going to give me a multiple of 14? Well, 4 times 7 gives me 28. That's the smallest multiple of 14 that I can get. So the order of 4 is 7. The order of 5 in Z9 is, all right, in Z9, 5, of course, I cannot find a multiple to give me exactly 9. And shoot, what do we get here? Essentially, what I'm looking for is the least common multiple of 5 and 9, which, thinking of it that way, is exactly 45, right? 5 times what gives me 45 then? Well, that's 5 times 9, so the order is 9. So now what happens is as I take this element and add it to itself, after I do that 6 times, this will be 0. After I do it 5 times, this will be 0. After I do it 7 times, this will be 0. And after I do it 9 times, this will be 0. So it works out very nicely that each of them will be 0, but I want them 0 all at the same time in order to determine the order of this element, right? When is that going to occur? So I say to myself, okay, well, I have to do it enough times that they all land, right? A multiple of 6, a multiple of 5, multiple of 7, multiple of 9, all land in the same spot. And I need to have it be the first time that it happens. So we're looking for the least common multiple of exactly these numbers here. So 6 is 2 times 3, 5 is just 5, 7 is just 7, and 9 is 3 squared. So I need the LCM of our numbers 6, 5, 7, and 9 is equal to, so I need a factor of 2, I need 2 factors of 3, I need a factor of 5, and I need a factor of 7. So if I go ahead and compute what that is, of course, I didn't write that down ahead of time, so let me grab a calculator and enter that. So we're going to get 2 times 9 times 5 times 7 is 630. Whew, big number. But you'll notice that this number is still smaller than if I had just multiplied all 4 of these numbers together, 6 times 5 times 7 times 9. That would have included an additional factor of 3. So that number would have been 1,890. So the order of the element 2, 3, 4, 5 is 630, not the product of all of these, which we said was 1,890. All right, so we found the order of a particular element. We want to determine the order of the element with the highest order in this group. Is there only one element with this order? So essentially, what we're looking at is in the individual groups, Z12, Z15, Z14, and Z9, each of those are cyclic, and so we can use the generator to be the element itself of the highest order, that order being 12, that order being 12, 15, 14, and 9. Once I have recognized that, I'm looking for just the least common multiple of these individual numbers themselves. So that's like in the example we looked at a little while back here, least common multiple of 2 and 6. We're looking for an element that has order, right? Least common multiple of that is 6. And we want to identify an element with that order. Well, I mean, we did identify an element with that order. The current question is not asking us to identify an element necessarily. All right. Here, if we're looking for the least common multiple of, let's see here, scroll back up so we can get those numbers. 12, 15, 14, and 9. We want to recognize how these can be written. 12 is 2 squared times 3. 15 is 3 times 5. 14 is 2 times 7. And 9 is, let's see here, 3 squared. There we go. So the LCM of these numbers, 12, 15, 14, and 9. All right, isn't that is that the one that we did earlier? 12, 15, 14, and 9. Yep, excellent. The 1,260. So I suppose we don't really need to do all that work again. 1,260. That is, it contains 2 factors of 2, 2 factors of 3, a factor of 5, and a factor of 7. Okay. We grab onto the highest number of appearances, or the highest number of factors. Not all of them, right? I'm not grabbing onto 1, 2, 3 factors of 2. I'm just grabbing onto 2 because that's the largest number of times that factor appears. All right, so we get this as our least common multiple. And then the question is are there multiple elements with that order? So this is the highest order element is, and notice that's not the order of the group, so this group is not cyclic. The highest order element is 1,260. Right, we said that the order of this group was 20,000 and something, right? So this is not a high order element, but it is the highest order element in the group. So if we are looking at that, let's see here, 1,260, are there multiple of them? Well, first of all, let's note that 1, 1, 1, 1, each of those are generators of the group. Therefore, they all have the highest order within the individual groups and therefore has order 1,260. We also have, let's see here, we also have we have other generators as well. So 5 is a generator for Z12. Let's see here, 4 is a generator for Z15. 3 is a generator for Z14, and 2 is a generator for Z9. 5, 4, 3, 2. Hey, that's cool. Also has order 1,260 because that's also a generator for each of these groups. So there are multiple elements that have that order. Okay? So it's not necessarily unique. It's not just that one. And is this element within that particular, right? If I use this as a generator to find a subgroup, is this subgroup the same as that one? Well, I don't know off the top of my head, but certainly in this, we can at least say that there's not just one element of that particular order. And whether or not they create the same subgroup or not, that I'm not sure of. We could take a look at that a little bit later, trying to generate this element from that one, for example. Ooh, yeah, right. Use modulo works out to be the same sort of work, I think. Yeah, interesting. Anyway, this is all that we really needed to talk about. How do we find the highest possible order? So, excellent. That's all I wanted to share for this video. So I'll see you guys back here in the office in just a little bit.